Okay, let's get started. Welcome to today's HO colloquium. We're very happy to have Professor Jiuhou Lei from the University of Science and Technology of China visiting us. And Jiuhou received his PhD in space sciences from Chinese Academy of Sciences in 2005. He then came to HAO as a ASP postdoc fellow and stayed on for 2 more years as a postgraduate scientist. Then he went over to CU, Aerospace Engineering Science Department, as a research associate. 2011, he went back to China, joined the faculty of the University of Science and Technology of China, and has been a professor in that school, the Earth and Space Sciences School. Since then, he has come back numerous times, collaborating with various collaborators there. and at HAO, and his research focuses on ionosphere-thermosphere modeling and space weather-related research. In 2010, he was awarded the Kospar Zeldovich Outstanding Young Scientist Medal. And in 2013, he received the Chinese National Science Fund for Distinguished Young Scholars. Without further ado, Jiuhou.
Okay, thank you, Hani, for the introduce. And I'm happy to come back. And at the border here is a very nice weather in summer, and spend a few months here almost every year. And I'm happy to see many friends here. And the talk I will give it. The title is Ionosphere thermal coupling in the Equatorial region. Specifically, I will focus on the Equatorial thermosphere anomaly. And first, I'd like to acknowledge many collaborators and from CU and from NCAR. You can see the name here. Include Jeff Sear and Vicky and many people in HU and Wen Bing An and Art and Ray and Ray Robo. And also many people name not mentioned here, and they helped me a lot to make this work happen. And Ben and Acid did a lot of work to help me debug the code. And this is the outline. I will start a little bit of background on the ion-neutral coupling. And this is a very last plot and given by Alan Burst. And this is a last two plot. Oops.
Oh, good. All right.
Okay. Maybe yes. So it's really nice to plot the neutral composition, the number density, and the ample expression, this the electron density in the same scale. You can see from 100 to 500 km, you can see the neutral density almost larger by a factor by order of 6, or even with the increase of the altitude go to 500, you can see larger by a factor 3. So the neutral atmosphere almost is the background of the plasma density. Any change in the atmosphere, and you will see this corresponding change in the plasma sphere. So we can expect the coupling between the neutral and the plasma. And here is one example show the storm case. This is November 7th, 2004. The largest storm happened around the end of November 7th, and you can see this alteration from Gooey's observation. You can see on the November 8th, you can see the definition of the alteration. The bottom panel shows the TC sapling around the orbit. You can see the TC definition and highlighted in two hemispheres. That reflects the coupling or the influence of the neutral density or the composition on the electron density. So this is a larger good example to demonstrate the coupling between the neutrals and ion. This is another way. Here shows the neutral wind response to ion drag. I just show you how the ion density or the electron density or TC respond to the neutral density change. Here you can see for quiet time and store time for two hemispheres. If you look at the store time or even quiet time, you can see the neutral wind see this kind of two-cell structure like convection pattern. And this because the ion drag effect and drag the neutral motion and has a similar pattern as ion convection. This is a large paper by Art and back 2003. So now we look at the neutral wind down to 140 kilometer, not 300 kilometer. Again, you can see the top panel show the neutral wind and bottom panel show the convection velocity. And if we zoom in the look at the BZ negative -2 condition, you can see the neutral wind also see these two cells structure, and this reflecting the and drag and at low altitude. So this is a few three examples to show how the coupling happen at high latitude, and not only the neutral influence and also the and drag the neutral, and although take many hours to have this kind of two cell structure. And in this talk, I will mainly focus on ion neutral coupling at low latitude. Specifically, two phenomena. One is the Equatorial Ionosphere anomaly. This is well known, go back 1914s, and also another phenomenon called the Equatorial thermosphere anomaly. And these two phenomena are very similar and may have some connection. And I just mentioned for the Equatorial thermosphere ionosphere anomaly, and you can see there are two crests and one trough. And here show the model simulation at longitude around the medical sector. You can see the trough around the -10 degrees and two crests sitting aside of the magnetic equator. And that means you're associated with the eastward electron field pushed and upward, and then due to the diffusion and the gravity force and accumulate around the magnetic latitude 15 latitude degrees. And also it change with solar cycle and the season and also geophysical conditions. And a similar structure is called Equatorial thermosphere anomaly, was discovered go back 1973 or 74, and by Healy and Mayer, and they used the August 6 satellite. Actually, in left panel show the temperature structure actually infer from the molecular latitude density, and you can see there are two stronger peak sitting around the geographic or magnetic latitude around 30 or 40 degrees, and there's a trough. In this plot, maybe you cannot see this feature very clear. If you organize the daytime data around the longitude, here is longitude. In each longitude, there is a one profile, the latitude profile at a fixed altitude. You can see they are almost from west to east. And there is a dashed line here. This is the magnetic equator location, and this very align with the minimum of the neutral density of the temperature very well. And also you can see two crests there. Although the latitude around 30 or 40 degrees is much polarward compared to Equatorial ionosphere crest. And this feature also found in the back 1991, and also reported found in the D2 satellite data and also AE satellite data. And this neutral temperature, you can see the dips or the trough around the magnetic equator. And although the crest is not very clear on this profile, and also the CHAMP satellite provide a large amount of data and can go back to with this feature again. And here show one of the plots from this study show the neutral density at the daytime around the longitude, this is latitude. Again, you can see very less. This is the dip or the trough around the magnetic equator, and there are two crests also align with the magnetic latitude. Remember this for what? Okay, Tim.
They're very different local time sectors, aren't they? These two.
For
one dayside and one is after sunset.
This around this is. Oops. I can't remember. This is around the sunset. Yeah, this is around 18 local time or 16 local time. Okay. They show many profiles. There's some 14 local time or 12 local time show this kind of feature. And the CHAMP set definitely can show look at different local time, different season. But for D2 set is hard because altitude change always, and you can see this kind of shape because the altitude and also longitude change. So it's hard to determine. And in this paper, only show three profiles. And so we you use the model to try to understand what the formation of this phenomenon and also the variability. The model we use are the TIEGCM, I guess many of you already know. And we mainly use two models. One is the TIEGCM and one is the time GCM. And from 175 meters to 5 or 600 can depend on solar activity and also solar flux. And this model solve the continuity and momentum also energy equation. We can get information of the composition and velocity and also the temperature for both and ion and neutral. Definitely we need to include solar flux and also the electric field and particle precipitation if not coupling with the magnetic with the MHD model. And also we need to specify the low atmosphere tidal force and for this study. And there are several mechanisms proposed to try to explain this phenomenon, include solar ion drag, go back to 1973, and it said because the ion density is low at the magnetic equator, and so less ion drag will cause larger flow of the neutral wind, that's the neutral gas. That means larger solar wind will happen at the magnetic equator, and then will push more heat toward sunset. So we'll see that causes the dip of the temperature here. And if this is the case, we'll see the temperature higher at the equator at sunset or at night time. A lot of mechanisms proposed by Tim and go back to 1997. And since the O plus or the electric density is higher at the crest region, suppose we'll get more chemical heating, especially the O plus and with nitrogen, molecular nitrogen recombination rate, and also a little bit from the molecular oxygen, and should we see more heating around the equatorial crest region. If this is the case, the latitude of these two crests should be align each other. And the third mechanism also proposed by Luomi and also we work with the team, and we use the early version of the CT at that time not coupling with the low atmosphere, low ionosphere model. So you use the empirical model to demonstrate the field line ion drag may be important to produce this feature. So we use the TIEGCM to do the sensitivity study to try to figure out what's the mechanism for the ETA and also the relative contribution for this mechanism, or there are some other mechanisms missed in the past. And we did a sensitivity study. We found that the solar ion drag and the chemistry cannot explain the ETA feature, and the chemical heating is too small to explain what we observed in the thermosphere temperature or density, especially for the crest. And we do see the stronger moderation or the contribution of the field line ion drag, especially for the trough. And we also found a lot of very important contribute to the ETA crest. That's the plasma neutral collision heating. And I will focus on these two. One is the field line ion drag. Why is it so important? And we look for the ion drag force, and we usually consider with the J cross B. That means the perpendicular ion drag. Always ignore the field line ion drag. That's for the first order approximation is correct because ion always move around the field line almost equal the neutral around the field neutral wind. But because the pressure force and also gravity, there's some difference between the field line velocity between neutral and ion. So the difference is the diffusion velocity. So if most of the model include the TIEGCM and CTIM, just include the perpendicular ion drag, that's the dominant term, but ignore the field line drag. If we include the field line drag, so what will happen? This is the one simulation we've done for the local time. Is 14 local time. Here show the plot for the neutral temperature at the altitude, and this is the latitude. This is geographic latitude. In American sector, you can see this without field line drag and with field line drag. When inclusive of the field line drag, you can see the difference mainly occur at the magnetic equator. The definition of the neutral temperature around 40 Kelvin degree, and depend which longitude we are looking at. And now you can see the crest and the trough and the crest. That's very similar with what observed. If without the fill and drag is sometimes you can see one peak, sometimes you even didn't see any peak, and at the mid latitude. So while when we include fill and drag, we cause this depletion, and this is a very busy plot try to explain the process. The top panel again shows the electron density. You can at the 14 log time, you can see the EIA crest and trough. And when include the fill and drag in daytime, the fill and drag is polarward. This is because the positive is the lossless. So you can see the polarward of the ion drag. When include the fill and ion drag, will accelerate the neutral gas in the polarward. You can see the wind change around 10 meters per second at around from the equatorial to around 20 degrees. And because the inclusion of the field and drag and will cause the pressure force and counteract with the ion drag, you can see the change of this pressure force almost offset with the field and drag. This is the residual of these two terms, and still you can see some forces there. And because of the wind, you can see the polar wind accelerate. That causes the diverging of the wind system. And in this case, you have the vertical motion of the neutral gas. That causes adiabatic cooling. And that's the whole process why we include the field and drag, cause the neutral temperature definition at the magnetic equator. So this is a diagram by week, and here again, because include the field line drag and cause the wind divergence, and also the pressure force try to counteract with the inclusion of the field line drag. So you can see how the divergence of the wind and how cooling region at the magnetic equator.
I don't understand if you have a divergence, do you expect a downward wind?
No, for this case, it's not because the density is much higher at the low level compared to high altitude. So the wind must be flow upward instead of downward. Yes, theoretically you can see go this way or go this way, doesn't matter. But the mass density or the composition is much heavier compared to up level. So the neutral atoms easier go this way rather than go downward. If you think the continuity and should be go upward easier.
You mean if you have a mass flux calculation?
Yeah. Yeah, the mass calculation, and you will go this way less downward because the mass is much heavier or denser compared to high altitude. So this is another way to look at this feature. This look at one particular altitude at 14 local time. This is the temperature and this mass density. Try to compare with the D and the CHAMP satellite. This is the default run for the TIEGCM. You can see a little bit bump there, but didn't see significant like observed ETA feature. When we include the field and ion drag, you can see the definition about 30 or 40 Kelvin degree. And now you can see the crest and the trough, the difference about 100 or a little bit less, depending on which longitude. And for the mass density, the ratio of the crest and the trough around 1.1, some 10% of difference between the crest and the trough. This is comparable with the CHAMP observation. So another question is well, if you go back, look at the default run, you still see a little bit of bump here. When you include the field line drag, it just drop. So we can say the field line drag only contribute to the trough, not for the ETA crest. So you will see because we have the trough here, you automatically will get two crests. That actually is not the case. If we go back to look at the CHAMP data, and not only the trough around the field, around the magnetic equator, actually the crest also overlapped by the magnetic field line. That is really cannot explain because you have the trough and then you have two crests. If this case, you will see the crest should be along with the geographic latitude because the solar depth angle and the solar heating should be mainly as geographic coordinates. So we go back to see what caused this crest, and we did a term analysis for the TIEGCM output. We found one process is very important to produce this feature is the plasma neutral collision heating, and this depends on the neutral temperature and also the difference between plasma and the neutral temperature and also the plasma density. And you can see at a high altitude, this term is very large and provoke more heating and will transport downward through the heat conduction process. And here many at in daytime, here you can see around 40 degree latitude, you see large peak. That's why we even didn't include the field line drag. You can see small or weak crest. That's the main reason. So in order to further to show the plasma neutral collision heating effect, we did a control run to turn off the collision and collision heating. That actually is not real, but we try to understand what the effect of this term. And these are two runs without plasma neutral collision heating. And the dashed line is for the default run without plasma collision heating and without field line drag. For the second run, without the plasma neutral collision heating and also but include the field line drag. You can see a lot of depletion is similar, but you can see a lot of crest is much equatorward move. You can see around the 20 degree or even less. If you put the electron density crest and chart, you can see almost at the same location. That's not consistent with observation. If we include the field line, include the plasma neutral collision heating and field drag, you can see this is the simulation. You can see the crest move to a much higher altitude. That's what we saw in the observation from D and TEM satellite. So from our simulation indicate the plasma neutral collision heating is a larger major contributor to the ETA formation, especially for the ETA crest. That's the at the same time, also other mechanism was proposed to explain, for example, third arrow tide by the Japanese group using Gaia simulation model. And they simulated the pressure and mass density show similar phenomena, trough and crest, but didn't see temperature and in all simulation. So this is not consistent with D2 and other satellite observation. So maybe the tide has some effect, but maybe it's not the major contributor for the ETA formation. Actually, we also look at how the third arrow tide contributed to the ETA variability. So we took the ECAM Canadian model at 100 kilometers to specify the third arrow tide as the TIEGCM low boundary. And here you can see the maximum amplitude around 30 or 20 degrees, and the second peak around the equatorial region. So use this as a boundary, we did a simulation here, just show you one example. This is NM2 peak density without third arrow tide, with third arrow tide. In these two fields, we cannot see the difference, but if you do the different field, you can see there's some effect. But how this third arrow tide to contribute to the ETA variability? So we did a couple of simulations. The top two panels without third arrow tide, the bottom two panels with third arrow tide case. And for each category, we did two simulations, and without field line drag, with field line drag. So again, this without field line drag and with field line drag. So you can compare without field line drag and without field drag with the same without third arrow tide and with third arrow case. And you can see a little bit different for the ETA feature we simulate almost not affect too much, but the third arrow include at the low bound. You can see a little bit different, but almost the same as compared with without the third arrow case. So while the Gaia model can produce the trough or the crest at in pressure and mass density, we go back look at their simulation. Actually, it's surprisingly their third arrow component has a maximum amplitude around the magnetic equator. That's when you in daytime anyway have 2 hours in upward has the downward or positive or negative phase, and you can see, for example, here you can see the negative phase here. But if you see the from the ECAM model, you didn't see this larger amplitude at the equator. That may be the major problem from this simulation. And the third answer may be not correct for the simulation. Try to get this feature, but anyway, the temperature is not consistent what we observed. So another thing we want to see is that we can simulate the ETA feature. So from the observation, we see a lot of variability. Here is one example. Here shows the plasma density from CHAM. This is in situ density around 400, and the tau panel from the accelerometer observation for the mass density. This for 3 days in E-cross. The time runs from right to left, and for 3 days. Because the satellite almost polar orbit, so you can, at these 3 days, the look time almost no change. So almost a fixed look time. So for this period, it's 18 look time. So plasma, you can see very well longitude variation. Definitely there includes some the geophysical condition change. That means the time evolution. And for the neutral density, you can see the crest and the trough. And for the plasma, you can see more regular, more stronger, and the crest and trough, and also equatorward compared to the neutral or the thermosphere equatorial anomaly. And for the thermosphere crest, you can see almost around 30 degrees, and for the plasma around 15 degrees. So you can see a lot the strong longitude variation. For the plasma, this is wave number 4. For the mass density, only wave number 1. But I will show the spectrum analysis here. This is for 2 periods. So for the plasma density, their wave number 4 already started for many years because the non-magnetized modulation. For the mass density, you can see the strong wave number 4, number 1 and also number 2. And the wave number 3 is smaller. Again, you have good increase of the wave number 4. So that means somehow the non-magnetized still have stronger modulation for the thermosphere. And we figure out for the wave number 1 mainly due to the offset of the geographic and magnetic pole. That's or the displacement of the equatorial, the magnetic equator between the geographic and the magnetic coordinate system. So we also did a little bit to try to figure out the longitude variation or the wave number 4 structure in the thermosphere. Actually, there are 2 studies to focus on the solar cycle, solar activity dependence of the wave number 4 in the thermosphere. One is from the Japanese group. They show the solar minimum condition for this wave number 4 in thermosphere, mainly because the direct propagation. In the meanwhile, almost the same issue in JSP, the paper show for the solar maximum is different compared to solar minimum, and they suggest the ion neutral coupling through the electron dynamic. That means when you have non-magnetized from the lower atmosphere and cause the electron density change, have this wave number 4, and then through the ion neutral coupling, cause the thermosphere have this wave number 4 feature during solar maximum, and is different with the solar minimum. So since we can simulate the ETA and the EIA, and we can further understand how the EIA creates and couple or decouple with the ETA creates. So we did a couple simulation. Here we showed 2 simulations. One is with magnetized only at the time GC low boundary. I forgot to mention this simulation done by the from the time GCM simulation. Another one includes both magnetized and non-magnetized. And here the simulations for 2 simulations, and this is non-magnetized and magnetized both. This is just magnetized. And the bottom shows the different field as a function of latitude and longitude. This is a fixed look time like satellite review the CHAMP did. And here shows the look time, 16 look time. This left panel shows the electron density, peak electron density. Right panel shows the mass density, indicated temperature field. And you can see this you can see the stronger wave number 4 feature in both ion and neutrals. And you can see the difference of these 2 fields. You can see the electron density is offset. That's expect because you have modulated electron dynamic process cause the vertical drift, and will push the ion upward, and will have gain more increase at crest and decrease at the trough, so it's offset. For the neutral, it's different. Also, you can see almost in phase, and you didn't see very clear the trough and light and crest feature. That means not related with you have larger electron density with larger neutral temperature change or neutral density change. But we also did for the this is kind of validation, and we took the differential field at for the electron density and the neutral density here, try to compare with the champ observation. Here again for the 16 nanometer, you can see the crest and we are offset out of phase with the trough. And for the neutral, you can see almost in phase, although a little bit phase different. If you put the neutral and crest together, you can see the phase different. You can see the red and the red and the 2000 line for the crest. You can see the phase different. And for the trough, almost in phase, a little bit phase differential there. And if you compare with the champ observation, you can see the auto phase almost consistent with the champ observation, and in phase for the neutral, crest, and trough. And again, you plot the neutral and crest together, you can see the phase shift, this consistent simulation. For the trough, almost in phase, a little bit around 30-degree differential of these two. And this kind of validation. So we go back to answer the question during solar maximum whether this longitude variation due to the ion neutral coupling first through the electron dynamic cause the electron density change and then go back change the neutral temperature and density. So we did a little bit like play a game, and here you did another run with magnetized and non-magnetized. But we replace the electron density from the run 1 with the magnetized early for each time step. That means for the electron density without this longitude variation, with many wave number 1 without wave number 4. Again, we can see this wave number 4 still in the neutral density or neutral temperature. That tells us it's not through the ion neutral coupling for this solar maximum condition, and the same as solar minimum condition. So direct propagation of the non-magnetized from the low thermosphere, low atmosphere, and propagate to upward cause this crest and trough change. And even you didn't see the difference between the crest and the trough. You also almost at the mid and low latitude always see this kind of wave, and also the crest. That means wave number 4 for the crest and the trough is in phase feature. So this is for the longitude or the non-magnetized modulation for the ETA variability. If you go back to this plot, you can see the neutral density show larger day-to-day variability. You can see here and even here, and that's because during this period there are a few CR or high-speed solar wind stream event occurred. But for the plasma density, you didn't see so strong a change. But for the neutral, it's very sensitive to the geomagnetic activity forcing. So we also did a lot of study, try to understand what's the effect of the geomagnetic activity affect this ETA variability. So we try to address a couple of questions, at least two. First is how the ETA feature affect by the direct heating. That means the geoheating and particle heating at high latitude during the geomagnetic activity is stronger. And the second is how is the ETA feature caused by the indirect process. For example, when a storm happens, the density increase or decrease. That means we have positive or negative storm happen, how this process change the ion neutral coupling and affect the ETA structure. So we did a simulation. We took the S satellite observation in 2006 HU storm that happened in December of 2006. But we didn't run this IMF condition in the real case. But we shifted the data to equinox because the ETA feature always observed in the equinox season. In solstice, because of the circulation, always destroy the two crest feature. Here for the day 80, we run the BZ lossward, always lossward. 5 Tesla, that means quiet condition, the geoheating is small. And during the initial phase, we already know, we studied a lot for this storm. And during the initial phase, the stronger positive storm happened when the BZ oscillate during the initial phase. So we try to look at how the ETA change by two processes. One is the direct heating, another is the change electric density and then change the ion neutral coupling process. Here we look at the quiet time. Here I showed you again. So for the default run without field line drag, this with field line drag case, this is quiet time. And if you look at the initial phase and geoheating, you can go up 1,000 gigawatts. And you took this latitude profile at 400, you can see the temperature, including low latitude and high latitude, all elevate by a few hundred Kelvin degrees. And again, you can see, although you didn't see the crest here, but you see trough. If you plot without field line drag, with field drag, during storm, you will see a little bit stronger trough for the depletion. That's because you change the neutral wind larger compared to quiet time cause stronger adiabatic cooling around the magnetic equator. But the crest definitely are masked because the storm tries to destroy these two crests because you have larger heating deficit at a high latitude. That's for stronger geomagnetic activity. I already mentioned from the observation actually correspond to very small or weak geomagnetic activity. That's CR and high-speed solar wind stream. So we also compared quiet time and with the simulation before the initial phase, you can see the BZ also oscillate, although the magnitude around a few nanotesla. And here we compare two simulations. One is all daytime 14 log time. This is the quiet time. You can see very less crest and trough. And took the simulation around BZ -3, and here you can see the trough didn't see change, but you can see larger crest. That means during weak storm or relative small geomagnetic activity occurred, and you can see the enhancement of the crest. That's the elevation of the highlighted forcing or cause the temperature change or the neutral mass density change. You can see the crest and with the difference between the crest and the trough is much larger compared to quiet time. So this the direct heating caused this equatorial crest, especially crest change. So another question, how the ETA affect through the change of the electron density. We already know during the initial phase, we found the electron density change by almost 100%. So we want to see how the electron density change also causes this, because the field line drag also related with the electron density magnitude, especially the frequency. So here we did a 3 round, all round done by BZ positive case, and that means for almost for quiet. But for round 1 is default round 2 with field line drag. For the round 3, still with the field line drag. But we replace the electron density at each step, but use the electron density during the initial phase. The density increased by a factor of 2. In this case, we can see didn't see too much change, but you do see a little bit definition at the trough region. That's because you have not stronger EIA peak and cause the adiabatic cooling is strong. That means the adiabatic cooling is a little bit strong compared to quiet case, but still, so the electron density change for this case, the positive ionosphere phase only play a second role in modulate this ETA structure, especially the trough. So this is go to the conclusion. So we found first is the field line drag acting. This is a follow-up study of the Belloomi, and we extend this study and look at more quantitatively compare with observation, and also this is with the self-considered carbon neutron and here for the field line drag mainly contribute the ETA trough, but has a needle effect on the crest. But we, furthermore, we found the plasma neutral kinetic heating is a major contribution for these two crates. And also, sensitive simulation indicate advertical heating during the fast solar wind at the equator or the solar wind jet at the equator, and chemical heating and also telltale tide only have some minor effect on the formation of the ETA, cannot replace the major feature of the ETA observed by the satellite of data. And we also look at the tidal and geomagnetic activity modulation. We do find the non-magnetized can propagate upward, and for both solar minimum and high solar activity condition, and the change the electric density only play the second role for both the tidal and also geomagnetic activity forcing, and that's the conclusion. I think I should stop here, and thank you. Take some questions.
Questions for Jiuhou?
The plasma neutral fusional heating, I mean, that's just dual heating. That's correct, isn't it?
Yes.
Is
the plasma collision, neutral collision not include the friction heating here. Yeah.
Or is it just heat transfer from the
just a heating transfer? Yeah. That depend on the neutral, the plasma and the neutral temperature difference. If no temperature differential, then you didn't see. So if you look at that time, these two not too much heating transfer. But daytime when you temperature different, and also you have larger electron density. And if you look at here for the plasma neutral kinetic heating, that's why you see larger heating poleward of the equatorial region. That becomes not only the plasma density matter, also depend on the neutral temperature difference. When you have larger electron density here, actually temperature is very low, and you don't have too much heating transfer between the neutral gas and the plasma.
So
yes.
It's the solar heating, the energy getting into the electron temperature, and then the electrons cooling and depositing their heat in the neutral gas. So it's not dual heating. It's the way that the solar energy is being redistributed by the high TE or TI.
Yeah, correct. That's the process. Yeah, the direct heat is from solar heating rather than the high altitude forcing. Yes, Tim.
One of the slides on the effect of geomagnetic storms seems to show that the crest seems to broaden in latitude.
Yeah.
Could you explain a comment on why the cause of
The
it?
the major process happens because when you have more or the geomagnetic activity is stronger, you have much stronger geoheating happen at high latitude, and through the advection heat process or the circulation, you transfer this heating to lower latitude. I mean, compare high latitude, and then you heat up the thermosphere, and you get higher temperature, and that means you have larger heating at the high latitude compared low altitude. That's why you have the crest will move poleward. You have gain more heating at high latitude compared low altitude, low latitude. Yeah, Tim.
The feature that you get after sunset that your area called the
ETA, ETM, yeah.
And the ETA, the dayside thing. Are you claiming that your mechanism is the same for both cases? Because it seems like the coincidence of the equatorial ionization anomaly on the post-sunset feature, the ETWA feature, is more aligned to the plasma density, whereas on the day side it seems displaced from the equatorial ionization anomaly. Are they different phenomena with different physical processes, or are you trying to claim that they're both the same?
That law we didn't see a difference between the two local time. Actually, we did a follow-up study to look at the local time and the seasonal variation seems can extend to 21 or 22 local time, rather than only constrained at the date 14 local time or 12 local time. So still seems because for the sunset local time, the electric density will still very higher, and you still have small solar heating happen, and the temperature is also very high at this period, and you have larger collision heating. I mean the heating transfer during this period. So you still expect to see the similar feature during sunset period compared with earlier noon time. But maybe other process we don't know yet. But right now we don't see any other mechanism to explain the different local time variation. Yes, Stan?
It seems to me that the trough or depletion at near the magnetic equator is the most prominent feature, both in the data and in some of the model simulations. And you can see very well in the plot that happens to be up right now, that delta WN in the lower right.
Right.
Very prominent feature. This crest enhancement seems diffuse, widespread, but that depletion, which of course causes crests right near the magnetic equator, is very clear. So what I'm wondering is, if you're attributing the biggest share of that depletion to vertical wind, could there be a composition component of the density change? Because a positive vertical wind will lead to a more molecular and hence less dense atmosphere. I'm wondering if there could be a composition component to that, and if we could look at that, if we looked at that.
Yeah, we look at the term analysis. Seems the major term is the adiabatic cooling term, and the V and times partial T, partial Z. So it's not associated with the composition change.
We could look at composition.
Yeah.
Is it changing?
Yeah, the composition definitely will change because you have vertical transfer here.
Exactly.
And you will see the composition change because you have vertical flux between these different levels. And yeah, definitely we can go back look how the effect of the composition. Yeah, Ram.
I was confused by your experiment where you doubled, as I understand, you doubled the plasma density, and there was no effect. Right?
There are some effect.
Shouldn't the effect double if you double?
No, this is not linear. This is not linear.
It's all linear, I think.
Which one?
The more plasma you have, the more is the drag, the more the throw.
No, this is actually the plot track can explain why this is not linear. And for example, if you double the the finite drag, you will not expect the wind acceleration will double because the pressure force always against the inclusive of the finite drag will not linear change of the neutral wind. That's the system. It's not steady state. It's almost change.
The more plasma you have, the harder it is to heal.
Yeah, it's not linear. And you can change by 10 degrees Kelvin.
Because there's more of it. The higher the electron density, the lower the electron temperature.
I'm wondering what happens if you only half the plasma density. Could you do that?
We didn't do that yet. Yeah, that's a worse experiment to do. For example, negative storm happen, what we'll see in the ETA. And it will be weak, but it's not proportional with the electron density change. And from the force you will expect, but actually this is a dynamic process. You change the collision frequency, change the finite drag, and actually the temperature and the lateral structure of temperature change and the pressure force will change, again. And also when the density change, actually, Stan just mentioned your plasma density, the temperature is different. You don't have too much heating transfer to the neutral gas. For example, you have positive storm, electric density doubled, and the temperature try to decrease by a factor 2, and then go back, you don't have too much heating transfer to the neutral gas. That's the dynamic process. That's not steady. If you fix the temperature, maybe you get the time of factor 2 of a factor 2 or factor 3 of depletion.
In your turbidal tide experiment, you use the Canadian.
Yeah, Canadian model output.
Of the turbidal tide. I didn't notice that you got midnight temperature maximum in your temperature plot, and I mean Russia's theory is that the enhancement of the turbidal tide gives you the MTM. I wonder what the magnitude.
Yeah, we got we just pop. I guess Rashid one of the referee, and yeah, and we do find the magnitude, the enhancement of the MTM due to the third delta. Just the magnitude only half of the observed by other satellite or compared with CHAM.
I was wondering if that might be the reason why you didn't see much effect from the turbine tide on the day side. That the magnitude or the way it was propagating up was not quite.
But even double the magnitude, we still didn't see the modulation of the turbine tide on the ETA. And I just mentioned the Japanese group was saw this definition in the pressure and mass and action. The third data from their survey is wrong.
So there are some observation evidence supporting the ECAM or the Canadian model, but not the.
Yeah, you did a study to compare the ECAM and with the safe data. It seems agree very well and in terms of the climatology sense. Yeah, but we didn't see the very strong amplitude at the equator. Instead, we saw the large amplitude at the mid-latitude or 20, 30 degrees. I guess it's considered with the YM simulation. Yeah.
Our question is, you have this plot showing the ETA and EIA.
Right. The observation.
And it seems that the EIA looks very
regular,
stable, while the ETA,
next one.
So, and maybe you explained this. You said there's a larger sensitivity on the neutral, or the neutral density to some geomagnetic perturbations.
Right.
Is that why?
Right. When you have the geomagnetic activity happen, and you have more heating, and the temperature will suppose will change somewhere, and the neutral density almost accumulate of the effect of temperature. When temperature say change a few Kelvin degree, and the mass density at 400 maybe change 20% or 30%. That's because the heating source maybe go down to 120, and all the scale had to change, or the neutral temperature change. So you accumulate from 120 to 400 all the way, you will see larger temperature change. For the plasma is different. Your neutral temperature, for example, neutral temperature change from the if the only thing is the temperature change, the peak height will not just move around. The peak density will not change. I mean,
so
from the barometric motion. Yeah.
Okay.
This is the electric density, not the peak density. I mean.
This is both from CHAMP, right?
Yeah, this is from CHAMP.
So it's up around 400 kilometers.
400 kilometers. Yeah.
I was thinking that if you have a big storm, you would, definitely see a lot of responses in the ionosphere.
Yeah, you will see larger change, but it's not as strong as the neutral. With the sense, if you look at the neutral density, when you have storm, you must see the density change by 100%, 200%, or 300%. Always like this. If you look at the busy source, you always see the TAD and propagate from the high to low latitude. But when you look at the plasma density, not corresponding, you will see the busy turning southward, and maybe later on you will see the negative storm, not such very good or one-to-one correlation between these two. So this is a different compared to plasma and the neutral. The neutral is very sensitive to the heating deposition. When you have a storm, and you will see the temperature change, although the composition will modulate a little bit.
And the local time is what?
This is 16 local time. Yeah, because satellite is polar, almost sun-synchronous satellite, and the local time doesn't change for these 3 days. So actually, what we saw here is longitude variation instead of this UT variation. And for the density, most for this larger enhanced, this because when you associate with the geophysical condition change, that's a UT change, something like that. So it's a difference between these two plots.
Okay. Let's thank Jiuhou again.
Okay, thank you.